Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into some really fascinating research coming out of Apple's machine learning group, SeedLM. It's all about compressing those massive large language models, or LLMs, to make them more manageable.
Compressing LLMs? That sounds like a huge challenge. I mean, these models are already so complex. What's the core idea behind SeedLM?
Exactly. So the basic idea is that instead of storing all the weights of the LLM directly, SeedLM uses seeds of a pseudo-random generator to encode and compress them. Think of it like a super efficient zip file for your model's brain.
A zip file for the brain. I like that analogy. So how does this pseudo-random generator thing actually work?
Okay, so for each block of weights in the model, SeedLM finds a seed. This seed is then fed into something called a linear feedback shift register, or LFSR, during inference. The LFSR efficiently generates a random matrix from that seed.
LFSR, got it. So it's generating a matrix on the fly. What happens with that matrix?
Right. This generated matrix is then linearly combined with some compressed coefficients, and that combination reconstructs the original weight block. It's a clever way to avoid storing the entire weight block directly.
That's pretty ingenious. So what are the real-world benefits of doing this?
Well, the big one is reduced memory access. By generating the weights on the fly, you're not constantly pulling them from memory. This speeds up inference, especially for tasks that are limited by how fast you can access memory.
Ah, so it's trading compute for memory access. Makes sense? Is it like a free lunch then?
Not quite a free lunch, but a very heavily discounted one. You're doing more computation, but you're saving a ton on memory bandwidth, which is often the bottleneck. And the paper mentions that they're leveraging idle compute cycles during inference, so it's really efficient.
Interesting. So how does SeedLM compare to other compression techniques out there?
That's a great question. A key advantage of SeedLM is that it's data-free. Many other compression methods require a calibration dataset to fine-tune the compressed model. SeedLM doesn't need that, which makes it much more versatile and easier to apply to different models and tasks.
Data-free is a big deal, so it generalizes better then?
Exactly. And the results they're seeing with Llama 370B are really impressive. They're getting zero-shot accuracy retention at 4-bit and 3-bit compression that's on par with, or even better than, state-of-the-art methods. And the performance is comparable to the FP16 baseline.
Wow, Llama 370B is a beast of a model. Maintaining accuracy at that level of compression is seriously impressive. What about hardware? Does SeedLM play well with specific hardware?
Yes, they did some FPGA-based tests, and those showed that 4-bit SeedLM, as the model size increases, approaches a 4x speedup over an FP16 Llama 2/3 baseline. That's a huge potential boost for deploying these models on edge devices.
A 4x speedup? That's incredible. So this could really open the door for running these massive models on devices with limited resources.
That's the hope. Imagine running Llama 3 on your phone without draining the battery in minutes. That's the kind of potential SeedLM unlocks.
Okay, let's dig a bit deeper into this LFSR thing. I'm still a little fuzzy on the details. Can you break it down a bit more?
Sure. So an LFSR is basically a shift register whose input bit is a linear function of its previous state. It's a simple circuit that can generate a long sequence of pseudo-random bits. The seed determines the initial state of the register, and from there, the LFSR generates a deterministic sequence of bits that looks random.
Deterministic but looks random. I see. So the seed is the key to generating the right sequence for reconstructing the weights?
Precisely. By carefully choosing the seed for each weight block, SeedLM can reconstruct the weights with high accuracy using this pseudo-random sequence.
Got it. And this is all done during inference, right? That's what reduces the memory access?
Exactly. Instead of loading the weights from memory, you're generating them on the fly using the LFSR and the seed. That's the core of the memory saving.
So what are the limitations? I mean, there's got to be a catch, right?
Well, the compute cost is definitely a factor. Generating those random matrices takes time, but the trade-off is often worth it, especially when memory bandwidth is the bottleneck. Also, finding the optimal seeds for each weight block can be computationally expensive, although this is done offline during the compression process.
Okay, that makes sense. So it's a trade-off, but one that can be very beneficial in many scenarios. You mentioned this is data-free, which is a big plus. Why is that so important?
Because it means you don't need a representative dataset to calibrate the compression. Many compression techniques require fine-tuning on a dataset that's similar to the data the model will be used on. This can be a pain to acquire, and if the dataset isn't representative, the compression can hurt performance. SeedLM avoids all of that.
So it's more plug and play, in a way?
Exactly. You can compress the model and deploy it without worrying about finding the right calibration data. That's a huge advantage for many applications.
And the FPGA results. A 4x speedup is nothing to sneeze at. What's the significance of using an FPGA for these tests?
FPGAs are great for this kind of thing, because they allow you to customize the hardware to the specific algorithm. This means you can optimize the LFSR and the matrix multiplication operations for maximum performance. It's a good way to get a realistic estimate of the potential speedup in a real-world deployment.
So it's not just theoretical, it's showing promise in actual hardware implementations. This is really exciting stuff.
Definitely. And the fact that they're seeing these results with Llama 370B, which is one of the most challenging models out there, is a testament to the effectiveness of SeedLM.
Are there any other interesting details in the paper that we haven't touched on yet?
Well, the announcement also mentions related readings on model compression and differential privacy. It seems Apple is doing a lot of work in this area, trying to make machine learning models more efficient and more private.
Differential privacy is another hot topic. So they're looking at both efficiency and privacy. That's great to see.
Absolutely. It's clear that Apple is taking these issues seriously, and SeedLM is a significant step forward in making LLMs more accessible and deployable.
So to summarize, SeedLM is a novel compression technique that uses seeds of pseudo-random generators to compress LLM weights, reducing memory access and speeding up inference, especially for memory-bound tasks. It's data-free, generalizes well, and shows promising results on Llama 370B with potential for significant speedups on FPGAs.
Perfectly summarized. It's a really exciting development that could have a big impact on the future of LLM deployment.
Definitely something to keep an eye on. Thanks for breaking it down for us.
My pleasure. And thank you all for tuning in to Tech Bytes and News. We'll be back tomorrow with another roundup of articles from Hacker News. Goodbye. Opening parentheses, closing parentheses.
Bye-bye.